Hello, I am Shreyas Ranveerkar. So our group will be presenting some of the AI techniques that are used in game development. Uh, in recent published games, we see that almost all the games use AI in some form or the other, like enemy chasing through obstacles. In fighting games, enemy attacking low damage attacks when player health is low, or auto difficulty setting in between the game, and etc. So using AI in games makes them more fun, real, and interesting. But AI that are used in game development are considered to be weak AIs. So here are some of the topics that we are going to discuss in this presentation. The first is finite state machine. The finite state machine is a machine or arrangement consisting of various predefined states. These states can be considered as game elements, uh, behavior, like the game character behavior, enemy behavior, obstacles, etc. So the states decide how the particular game element will behave when a particular event happens. Like in Mario game, when the Mario gets the uh, magic mushroom, which is a event, then he gets transitioned to other state. So he gets bigger, invincible, and faster. So this behavior transition is set by different conditions. Let's take example of Pac-Man game. The ghost behavior in Pac-Man game is a finite state machine. We can see in the diagram that the ghost initially starts with the chase behavior, where they try chasing the Pac-Man. But if the Pac-Man eats the energies, they get transitioned to frightened state and they start running away from the Pac-Man. And if in this condition Pac-Man hits them, then they get disappear, and if not and the energy drains out, then they again goes to their initial chase condition and they try chasing the Pac-Man. So even in game engines, like in almost all the game engines, in their animation system, uh, these states are used to change the uh, game elements animation or game elements uh, visuals or the game elements graphics. Next is fuzzy logic. So fuzzy logic is like solving problems like how we humans do linguistically. For example, very cold, nearly cold, or cold, etc. So we don't always use concrete temperature values to describe any temperature condition. We use so using fuzzy logic involves three steps, that is fuzzification, fuzzy rules, transition, and defuzzification. So fuzzification is like mapping uh, crisp values or discrete values to fuzzy input. This is achieved by by membership functions known as characteristic function. We can see at the bottom of the screen that if a particular value is less than x naught, it gets to false, otherwise true. So to add depth or to add degree to this transition, uh, we can see we can see this in the second graph, that a particular value has some degree with respect to other values. This is obtained through fuzzification. So the next step is fuzzy rules. So fuzzy rule is a conditional if and then statement, if x equals a, then y equals b. It's the rule which governs the operation of fuzzy logic controller. So in this statement, in x and y are classical mathematical variables, and a and b represent values with fuzzy sets and are logical continuous variables between 0 and 1, as opposed to discrete variables that are between 1 and 0. So the next step is defuzzification. So this defuzzification is a process of taking fuzzy output members or the fuzzy output that we obtained from the crisp input and convert them back to crisp numerical output. So this is obtained through graphs, through considering the area under the graphs. Uh, there are various methods like center of gravity of the graph area, or center of sum, center of largest area, and weighted average, etc. That's it. Thank you.
Hello everyone, I am Sourav. I am here to talk about genetic algorithms and its application in game development. So a game designer's job is to create a challenging game environment for the player. So creating a truly balanced and challenging game for players of different skill levels can be a difficult task. Genetic algorithms can be of great help here. They are simply a method of finding an optimal solution to a problem in hand. They basically involve a trial and error approach. You essentially populate the game world with many possible solutions and then determine which solutions work the best. Not all, but genetic algorithms work best when the elements of the problem are somewhat unpredictable. So this allows the game AI to adapt to a situation the game designer might not have been able to predict. Implementation of genetic algorithms in games can be broken down in 4 steps. Um, Creating the first generation, um, ranking the individuals of the population based on their fitness, selecting the fittest individuals, then evolving amongst them. So in coming to the first generation, each individual in the first generation represents a possible solution to the problem at hand. It is important to create an initial diverse population uh, because if the individuals are too much alike, the genetic process will be less effective. And then the fitness function tells us how best the individuals solve the problem at hand. Um, and in the selection step, we choose the individuals whose traits we want to instill in the next generation using the fitness function. Um, Finally, in the evolution step, we take individual chromosomes from the fittest members of the population and begin combining them. At this point, it is also important to introduce random mutations. Once the evolutionary process is complete, we again return back to the fitness tracking step. This iteration continues until we have generated reasonably fit individuals which can provide good response to the situations in hand. Um, we also consider the case of a hypothetical multiplayer role-playing game. Here, genetic algorithms can be of much use, wherein a computer-controlled adversary must respond and change due to the player behavior. In this game, the players would be able to choose from many different types of character classes and abilities. So the various combination of class and weapon types would make it difficult for a game designer to create a single type of computer controlled individual that would be a challenge to every type of player controlled character. For example, one possible situation would be when the player attacks a computer controlled character with a magic weapon. We can create several possible responses to this player action. The character would attack back the player in response, or can attempt to flee, or can attempt to hide, etc. Uh, so, um, so we would assign each situation and its response to a chromosome. And if this chromosome is set to create an attack response, the player will be attacked using the magic weapon. However, what if this scenario always lead to the defeat of the computer controlled character? In that case, the character would be deemed less fit and therefore less likely to pass on that trait. In successive generation, this scenario would lead to a different behavior such as retreat whenever the player wields a magic weapon. We can also see the possible scenarios and behaviors which the character can be in, and the computer control character is represented by AI creature class here, which has a chromosomes variable, which essentially is an array of the chromosomes, which we have discussed so far. Also, we have a population, which is an array of these AI creatures, um, which essentially comprises the first generation. We also create individuals. I mean, we also create these AI creatures by randomly assigning responses to different situations. We can see them being assigned different responses when in the scenario when they are attacked by a group here. Um, then ranking the fitness, we need some way to quantify and measure the level of challenge provided. So role-playing games typically assign hit points to each character. These hit points are reduced as the character is injured during the battle. So we use the ratio of damage done to the damage received as the fitness of the individual and sort them from most successful to least. And in the final evolution step, we use the traits of the individual in the we use the traits of the individuals in the lower array elements to create the next generation. We can see the visual representation of the evolution and the crossover that is happening and the implementation here. So we alternate between the parent indices to mix up the parent chromosomes. We also introduce random mutations to improve upon the previous generations.
Speaking about variation techniques. Variation networks are graphs that compactly represents the relationship between random variables for a given problem. These graphs aid in performing reasoning or decision-making face of uncertainty. So such reasoning relies heavily on bias rule. So let's consider the flowing diagram. In the flowing diagram, the nodes labeled T, T of R, and L represents the random variables. The arrows connecting each node represents the causal relationships. So we can think of nodes at the tail of the arrows as parents and nodes at the head of the arrows as children. Here the parents cause the children. So the figure shows that log is caused by trapped or treasure or both trapped and treasure. So we should be aware that this causal relationship is probabilistic and not certain. For example, the chest being trapped does not necessarily always cause the chest to be locked. There is a certain probability that trapped might cause locked, but it's possible that trapped might not cause locked too. So if we measure the strength of connection between events in terms of probabilities, each node has an associated conditional probability table that gives the probability of any outcome of the child event given all possible combination of outcome of its parents. So let's consider trapped can be either true or false. Let's also assume that treasure can either be true or false. So if lock can take the values true or false, we need a conditional probability table for lock that gives the probability of lock being true, given the combination of values for trapped and treasure, and the probability of lock being false, given the values for trapped and treasure too. So let's move on to the next slide. The flowing conditional probability table is for locked. So in this table, the first two columns shows the combinations of values for trapped and treasure. The third column shows the probability that logged is equal to true, given the combination of values for trapped and treasure. While the last column shows the probability that logged is equal to false, given each combination of values for trapped and treasure. The symbol used indicates the conjugative binary of an event, which means that if P of T is the probability of trap being equal to true, P of negation of T is the probability of the event being equal to false. So as the number of possible values of these events get larger, or the number of parent nodes, let's say given the child node goes up, so the number of entries in the conditional probability table for each child node increases exponentially. Let's move on to the next slide. So we can make three basic type of reasoning or inference using Bayesian techniques. So let's consider the flowing figure. The network on left is called a causal chain. In this case, it's a three-node chain. The network on the upper right is called a common cause network. It's more commonly referred to as the naive Bayesian network or the Bayesian classifier. The network on the lower right is called the common effect network. The three basic types of reasoning as follows. So one is diagnostic reasoning. Diagnostic reasoning is probably the most common type of reasoning using Bayesian networks. So this sort of reasoning along with Bayesian classifier is heavily used in diagnostics. So for example, referring to the network on the upper right, A would be a disease and B and C symptoms. So given the symptoms presented, the doctor could make the inferences as to the probability of disease being present. And the other one is predictive reasoning. Predictive reasoning involves making inferences about effects given information on causes. For example, if we refer to the network on the left, if we know something about A which causes B, we can make some inferences about the probability of B occurring. And the other one is explaining away. Explaining away involves common cause networks, as shown in the lower right. Let's assume nodes are all binary. That is it's true or false. So if we know C is true and we know A and B cause C, given that C is true, we could raise a probability that A and B are also true. However, say later we learn that B is true. This implies that probability of A occurring actually decreases. So this brings up some interesting characteristics of Bayesian networks, namely independence and conditional dependence. Of billions of neurons, each one connected to thousands of other neurons to form a complex network of extraordinary processing power. Artificial neural networks attempt to mimic our brain's processing capability. The AI community uses many different kinds of neural networks to solve all sorts of problems, from financial to engineering problems, and many in between. Neural networks often are combined with other techniques such as fuzzy systems, genetic algorithms, and probabilistic methods. Let's move on to the next slide. Neural networks. So the structure of neural network, there is no restriction on the number of neurons within each layer. Every neuron from the input layer is connected to every neuron in the hidden layer. Further, every neuron in the hidden layer is connected to every neuron in the output layer. Also, every neuron with the exception of the input layer has an additional input called bias. Inputs, inputs to the neural network is obviously very important. Without them, there is nothing for a neural network to process. Weights. Weights in a neural network are analogous to synaptic connection in a biological network. The weights affect the strength of a given output and can be either inhibitory or excitatory. It is the weights that really define the behavior of a neural network. Activation function. An activation function takes the input to a neuron and operates on it to produce an output for the neuron. Bias. The bias term shifts the input along the horizontal axis of activation function, which effectively changes the threshold at which the neuron activates. The bias value is always set to 1 or -1, and its weight is adjusted through the training, just like all other weights. This essentially allows the neural network to learn the appropriate threshold for each neuron's activation. Output. The choice of output neurons for a given neural network is problem specific. The training of a neural network. The aim of training is to find the values for the weights that connect all the neurons such that the input data generates the desired output values. Training a neural network is an optimization process in which we are trying to find the optimal weights that will allow the network to produce the right output. So finding the optimum weight is an iterative process. So starting with the training set consisting of input data and the corresponding desired outputs. Initialize the weights in a neural network to some small random values. With each set of the input data which we fed into the network, we calculate the input. And we compare the calculated input with the desired output and compute the error. And we adjust these weights according to the error and we repeat the process. So we can execute the process in two ways. One way is to calculate the error measure and adjust the weights for each set of input and desired output data. And then move on to the next set of input or output data. And the other way is to calculate the cumulative error for all sets of input and the desired output data in the training set. Then adjust the weights and repeat the process. And this each iteration is known as an epoch.
Hello, my name is Muhammed Haneen. Let's move into the topic basic pathfinding, which is one of the topics that utilizes AI in game development. In general, the shortest path is the line passing through initial point and destination, like figure 1. This type of path known as line of sight path. Line of sight path won't be always possible due to the obstacles in game world. One of the solutions at this situation is random movement, which is highly inefficient. One of the efficient method is tracing around the obstacles. Figure 2 shows our object initially moving at the line of sight path, but when faced with an obstacle, it traces around it. During the tracing, if we again met with the line of sight path, choosing that path to the destination will give a relatively good result, as shown in the figure 3. The most efficient solution using tracing method is obtained when we check whether a line of sight path is possible at each point of trace. It is shown in the figure 4. Having too many movement possible is a general scenario in most games. But when we try to pathfinding in this situation, it will place a huge burden on CPU. One way to resolve it is using waypoint navigation, which uses pre-calculation and inexpensive pathfinding methods. Let's see how it works. In figure on the left side of the screen, we can see game world is divided into several areas and each area is assigned a node. The nodes are assigned in a way that at least one neighboring node is on the line of sight of each node. These nodes are named and connected by line of sight path as shown in the figure on the right side. Now let's see how the navigation works. Node closest to the initial point is taken as starting node. Node closest to the destination is taken as endpoint. So here in this navigation problem, our objective is to find path from B to G. We'll do it using the node table, which lists the next node it has to intersect while traveling from one node to another. For example, for A, if we have to move to any another node, we have to pass through B. Using this, we will try to find the path from B to G. We have to move from B to G. We have to first intersect at C. From C to G, we have an intersection at E. E to G, we have an intersection at F. F can directly move to G. So the path we will find will be B, C, E, F, G. Let's move into the A-star pathfinding. A-star algorithm is one of the best pathfinding algorithm available in game development. A-star algorithm is guaranteed to find the best path between any starting point and any ending point, assuming the path exists. It is also a relatively efficient algorithm. First step of A-star pathfinding is defining a search area in a way the algorithm will work in game world. The game world is simplified by placing nodes throughout the game environment. We also must reduce the number of nodes to a minimum by simplifying game environment. A-star algorithm works best in game that uses simple movement. For example, the game that uses tiled world just forward, backward, up and down movement. The pseudocode for A-star pathfinding is given. A-star works by starting at a node and branching out until it reaches the destination. Here in the figure, position of the spider is taken as the initial point and as of the human as the destination. The black colored blocks are the obstacles and we have to find the path by avoiding this obstacle using A-star algorithm. The A-star algorithm selects the next node by considering the score of each node. Score is the sum of cost from initial point and heuristic value. Here we will take one step from initial point cost 1 unit and the number of steps required to reach the destination from a particular node without considering the obstacle is taken as heuristic value. If we look into the figure, we can see all the 8 direct neighbors of initial point have a cost 1, but their heuristic value may differ. If we come into a situation where the open list is empty without reaching the destination, we can conclude that no path exists. It is a dead end. In games, generally, the cost of each step in different direction may have a different value because, for example, in a normal road, it will take less cost, but in a muddy road, it will take a lot of effort to move, so the cost will be higher.
The one big thing in game AI is learning. All non-player characters act in a predetermined way is a boring scenario. By the time game reaches a particular stage, the non-player characters should also evolve depending upon what the AI system learned to make the game less predictable to the player. The techniques for learning and reacting to the character's behavior fall under the deterministic AI. Most of the non-deterministic AI methods that are available are still can be efficiently applied in practice. Several games such as Creatures, Black and White, Battle Cruiser, etc. used a non-deterministic method successfully, creating renewed interest in neural network, genetic algorithm, and probabilistic methods. For practical purpose, they still used a hybrid of non-deterministic and deterministic method. In this way, you can at least isolate the part of your AI that are unpredictable and more difficult to develop, test, and debug, while ideally keeping the majority of your AI system in a traditional form. That concludes our presentation on AI in game development. Thank you.